Alright, we're on the final stretch, where now we're going to apply all of this complex analysis stuff that we learned this episode to this funky looking integral, where we're kind of unsure what to do with this denominator, because you can't u sub because there's nothing to substitute. You can't integrate by parts because you're just going to continue taking derivatives and integrals. You just won't end up anywhere with integration by parts. Basically, any standard calculus technique will not work here. So, well, we can start off with saying that this is the equivalent of 1/2 integral from negative infinity to infinity of 1 over x squared plus 1 squared dx. And why that is because 1 over x squared plus 1, or with a squared, whatever, it's a symmetrical function. It's gonna probably end up looking somewhat, it's probably gonna look like this. Where the area of this side here is going to equal whatever's on the left side, because x squared is the same as a positive number or the negative version of that number. So it's an even function. So what do we do after that? So the trick is to integrate this in the complex plane. So we have the closed loop line integral of 1 over z squared plus 1 squared dz over the closed contour of our choice, because the problem didn't give us any contour, so we get to choose our own. And in this case, I'm going to choose a semicircle that only encloses one of the two singularities. We'll just choose I, because remember, singularity, if you just do the math quickly, our singularities are I and negative I. So we can surround one of the singularities. So then we'll end up getting well, first of all, let's factor. Let's just get a bit of extra factoring practice in. So z squared plus 1 equals z plus I, z minus I. So this is 1 over z plus I squared, z minus I squared. And now z plus I can go on top because it doesn't really change anything, this contour. So we have closed loop integral of 1 over z plus I squared over z minus I squared dz equals, well, we can remember our formula. We can just append this n factorial over 2 pi I equals to f to the nth derivative of z naught. So we remember n is this minus 1, since this is equal to n plus 1. So we get 2 pi I over n factorial f to the nth derivative z0 equals to this part of the integral. So that's 2 pi I over 1 then the first derivative of f with respect to z, then we can plug in z naught. Remember, z naught is going to be I, since that's a singularity enclosed. So the first derivative of z plus I squared, we already calculated this earlier, -2 over z plus I cubed. So we can multiply that by -2 z plus I cubed. We can plug in our singularity I, 2 pi I times -2 I cubed, 2I cubed. So we get -4 pi I over -8I. That's pi over 2. But remember, we're only integrating over half of that. So what we're doing here is we're taking this integral over this contour. We're having a radius r, but we're making r approach infinity. So we're still taking half of what we have here. So yes, pi over 2 is this integral without the half. So our actual answer is going to be pi over 2 times 1/2. That is pi over 4. That's our final solution.